Can you guys hear me okay? And you guys can all, okay. You positioned well to be able to see me still behind the pillar. Awesome. So hey everyone, I'm Jeremy. I am from Isovalent, and I'm really excited to talk to you all today about eBPF and Tetragon. We're going to be talking about some adventures in the kernel, and I'm going to be moving through slides quick, so going to go ahead and get started. So I want to spend some time today talking about some of the background and overview and architecture of Tetragon, how the open source Tetragon project uses eBPF for security observability, some of the kind of principles behind eBPF itself. You know, what are some of the benefits that eBPF offers over traditional security tooling? And I'm sure quite a few of you are seeing the rise of eBPF in the last maybe few months for you, or maybe last few years as well. And then I want to talk about some of the core principles behind the Tetragon project. And then I was going to do some use cases, but I think it'd be more fun to actually talk about the XC-util CVE from a couple months ago. So we'll spend some time looking at a YAML policy, talking through that, and if there is time at the end, I'll just do a quick demo of how to install Tetragon, how to install a tracing policy, how to actually look at some processes. Just in the first couple minutes, what are some of the fun things you can do with Tetragon? So let's get started. Maybe you're more familiar with some of the stuff on the left side in terms of the Isovalent project landscape. Maybe you've used Cilium, the Cilium CNI, maybe the Cilium service mesh, or maybe you've actually used Hubble for extracting observability. Today we're going to be talking about Tetragon. So Tetragon is focused on security runtime. At a high level, it's an agent written in Golang. It can work on any Linux distribution. In Kubernetes, it is deployed as a daemon set. And it uses eBPF programs to do the collection in the kernel. So hopefully that gives you a good base understanding of what the Tetragon project is. Just to kind of step back a little bit, I think some of you may be new to Tetragon. It hit its 1.0 mark just last year in 2023. We're seeing quite a few people use it in production now, but I wanted to give a quick background on the history of it and just kind of see the lineage that it's building on. So in 2016, actually, was when the Cilium project first started. And then in 2018, Cilium hit its 1.0 mark. In 2020, the very first lines of Tetragon were written. In 2021 and 2022, we saw Tetragon become open sourced. We saw a lot of people start to develop on it and start to talk about it at conferences. And in 2023, we saw it hit its 1.0 mark. And the main reason I say all this is that I think it's easy to see a project like Tetragon and think, oh, it's only been around for 18 to 24 months, kind of in the news cycle or kind of in the CNCF landscape. But it's really building on almost a decade of eBPF experience and that background in Cilium as well. So even though it feels like it just hit its 1.0. It's really having quite a few production users. It's really ready to go. And I think as far as the eBPF landscape goes, it's really exciting to be able to use something like this to instrument runtime observability at such a low overhead. And I'm sure a few of you will be interested in the benchmarks and stuff that we'll get into later. So quick overview of Tetragon. So I'm going to give you two diagrams of the architecture. I'll give you this one and then this one. Some people like this one, so I share both, and some people like the other one. It's just a matter of preferences. But essentially on the left side here, we have our Tetragon agent sitting in user space. So this is where you'll control your eBPF programs. You can take out the events, put them in your SIM or your metrics. Someone was asking me earlier about transferring events to Prometheus. So it's quite easy and interactable. You can apply your policies as CRDs. In the middle, we have the Linux kernel, and this is where all the fun stuff happens with eBPF. This is where we deploy our programs. This is where we extract the events. We can look at syscalls. We can look at namespace events. We can look at in-out activity around file access and file monitoring. Some really interesting stuff, but this is where we really push as much logic and aggregation is into the kernel itself. And I'll talk about that in a minute. Okay, so this is the second side of the architecture. Like I said, it's essentially the same thing. On top, we have the Tetragon agent here. This is sitting in user space. And then what we're doing is we're applying a policy or an eBPF program into the kernel. And what it's doing is collecting all of this security significant information that we might be interested in. Maybe we want to alert on file access activity, or maybe some syscall activity, or even network activity like HTTP, DNS, TLS, TCP, UDP, all of this and more we can start to instrument and look at. And one of the key things I want to kind of pause on here is a few of the benefits around Tetragon and eBPF is what we'll get into today. But there's just a few from a high level that I think are important to note. One of those is the Kubernetes awareness, so being able to tie back specific actions to specific pods or namespaces or workloads that we're interested in. And then also inline enforcement, and we'll talk about that in the next couple slides when we talk about some of the benefits of eBPF. We can always come back to this later as well during the questions if you're interested in how to deploy Tetragon, how its architecture works. But hopefully from a relatively high level, this gets you there. And one thing to note before we move on is what we're really interested in from kind of a resource utilization perspective is one of the higher cost offenders from a security perspective is anytime you see an event in kernel space and you want to take action on it or alert on it or bring it up to user space, crossing that kernel to user boundary is where we see the highest amount of CPU or memory cost. So the whole ethos and principle behind Tetragon is push as much logic into the kernel as possible. And we'll see why with the next few slides. So I'm just going to spend a couple slides talking about the principles of eBPF. One of them just to kind of build off that last slide around Tetragon as the agent space, and then the eBPF programs in kernel space. Why is that? Why do you want to use eBPF? What are some of the benefits? And one of the key one is this in-kernel filtering, we believe is really kind of the core essential piece of getting low overhead from a security perspective. When you're dealing with an extremely high volume of events, this can be extremely costly to cross that kernel to user space boundary constantly. So that's kind of the two key offenders here we're seeing is exporting data from a security perspective and then also managing the kernel ring buffer. So anytime you're moving that event back and forth, you're actually using a kernel ring buffer to move it between user space and kernel space and vice versa. And it does have an upper bound. So essentially what we want to do is instead of use that to just transfer high volume events, we want to use it as what we'll call like an alerting channel where we're in the kernel with our eBPF program, we're constantly monitoring, but we're not actually moving an event into user space until we actually have to, until we say this is significant to us. And what that does is it makes it really trivial to monitor extremely high volumes of event in the kernel without actually moving them, because you're actually not taking up the majority of the cost by moving that event over. Another thing I want to talk about is I think when we think of the kernel and we think of it from a security perspective, maybe the first thing you think of is a syscall. Maybe part of that is back in my days of just like writing like allow list and deny list for seccomp or something like that. But I think a lot of people really think of syscalls, and the kernel is so much more than that. We can touch essentially everything, and that's kind of one of the core things we'll see also is Tetragon allows you to observe everything, every process, the binary behind that process, the parent process that spawned that process. You're able to look at file activity, network activity, operating system activity as well. And one of the key things here is when you have all of this information, you can start to paint the picture of what event happened, who was involved with it, and what are kind of the preceding events that led to this malicious activity. And we'll look at a process tree later on where we build out this story of what happened, how did it occur, and what was the end goal of the attacker. The other thing is this is a security conference. I think we would be remiss if we didn't talk a little bit about enforcement. And that is one of the key benefits of eBPF here is instead of having to move an event into user space, decide whether to act on it, and be reactive about a policy, eBPF sits in the kernel and it's there right as the call happens. So you can take inline action. And Tetragon supports a couple models for that. So you can override the value so it returns null, so the value doesn't ever actually execute, or you can actually kill the process itself. So in terms of thinking of this from an enforcement perspective, instead of just monitoring our environment, we can actually go out there and take action and enforce policies that say, hey, this is actually against our whatever it may be, and in line as the signal is executing, actually kill the function from executing. Sorry. Awesome. All right, so we've talked a little bit about the background of Tetragon. We've talked a little bit about the architecture of Tetragon as well. And then we talked about some of the basics of eBPF and why it has that advantage from, say, moving events over from kernel into user space, some of the advantages from an enforcement perspective. I want to spend a little bit of time talking about some of the core principles behind the Tetragon project from an open source perspective. These are kind of the three things that we feel like gives Tetragon a unique advantage over some of the other tools out there, and I'm going to walk through each of these shortly, but really just from a high level, the Kubernetes awareness piece, that simplified observability piece, and finally the minimal overhead where we'll talk about some benchmarks. So the first one is, I think a lot of people struggle with Kubernetes awareness in the world where, dynamic IP addresses are getting spun up and spun down. It's really hard to rely on this kind of legacy technology that doesn't have the pure metadata that Kubernetes offers to be able to tie together an event to a specific workload. And what we'll see with Tetragon is it has really rich information in its JSON events. So just to kind of break down this event really quick, what we have here is just a pretty simple JSON event that Tetragon can create, but what's inside it is increasingly interesting. So right here we have the process side. We can see the process ID. We can see the binary that's run. We can see someone NC, that's a netcat command. So I think someone earlier was talking about netcat commands on one of their attacks. We can see the argument that it was executing with, and we can see all the metadata information about the pod, the namespace itself, the name, the container ID. We can see that it's running with the pod labels crawler and part of that Docker as well. And then over here, we can see the permissions it ran with. So we ran with the permitted permissions here and then the affected permissions. So affected permissions are higher. Maybe someone was escalating their own privileges and running at a higher privilege than they should have been. And then on the right, we have this really interesting information around the process IDs. So this is starting to build that map of what happened when, what was the preceding events to this. And this is a JSON event. It's a little hard on the eyes, but this is really interesting. So let's go ahead and put this in a different way. Same information, but different format. And we start to see the storyline going of someone running a command to get into one of our maybe Elasticsearch buckets and trying to exfiltrate data out. So let's break this down again. We have that metadata information of the namespace and the pod name. We can see the container runtime itself start. This is a containerd runtime. Then we have the process tree. And what we have here is all that rich information stemming back from what spawned what next process. Here we can see someone reached out to twitter.com and then started or ran a JavaScript, started that ncat command, and the netcat command reached out to notreverseshell.com, starts to reach out to our Elasticsearch bucket, get all of our good information, and then the next phase is going to be trying to perform lateral movement and then exfiltrate data itself. So all of this is coming from that single JSON event of that netcat command, but what we're able to do is tie this network layer data with this runtime binary process information to get a really rich context of not just, hey, this occurred there, but really being able to understand the exact workload, the exact binary, the who, the what, the when, the how behind all of these malicious activities. So that's the first piece of the Kubernetes awareness. The second thing I want to talk about is the simplified observability piece. So this is kind of the fun benchmarking section. I'll walk you through maybe 3 or 4 different benchmarks here. And the first one, we'll do minimal overhead next, and that's the benchmarking one. The simplified observability piece. So this one, I want to pause for a moment. I think back in the last few years of me trying to actually get a handle on my Kubernetes environment from a security perspective, I think all of us kind of feel this way where Kubernetes doesn't really give us the tools out of the box to handle our security. From a security perspective, the most we really have is maybe pod security standards or pod security policies, which I think PSPs got deprecated recently for PSSs. But really it's on us as operators to own our Kubernetes environments. And I think one of the big things that Tetragon's trying to solve for here is make it easy out of the box for people to simply apply policies and get that strong understanding of what's going on in my environment without having to dig into too many different resources or scramble and piece together different tools. So what we have here is a few different policies ready to go on the Tetragon docs. So these are just easy apply policies to see what processes are running, see if anyone's running malicious syscalls or something like that. In fact, let me get out of the PowerPoint, because anytime you can get out of a PowerPoint, that's probably a good thing, right? Let's do this. The policy library, let me just show you one of these. So maybe you're interested in security sensitive events. Maybe you're interested in monitoring for set UID syscalls. So if someone's doing the set user ID or set GID syscall, it's probably them trying to run their permissions as that effective user. So this is something that you might be interested in from a security perspective. But maybe you don't want to actually know how to write your own YAML policy. I'm not sure how many of you enjoy writing YAML. I don't, spoiler alert. But what we have here is kind of ready to go YAML policies for you to apply with Tetragon. So what we can do here is simply grab, copy it, and just put it in our environment, and it's ready to go. And I can talk about this a little later as well. If you're interested in talking YAML, I don't know why you would, but if you're interested in talking YAML, we can talk more about these policies. But there's a whole library of these, and it's continuously growing from the community. And I think this is a really strong piece of what Tetragon's growing to as a project, which is being that simple, out-of-the-box observability tool for Kubernetes. The final piece is minimal overhead. So this is where we'll talk about the benchmarking, of course. So in advance of 1.0, we did quite a few different benchmarks. We did one on process execution tracking. We did one on a high volume of file activity. And we did 2 tests using netperf for TCP CRR. So we wanted to see a range of things. What's the cost of just kind of observing every process? What's the cost of a high volume of file monitoring? And also, what's the impact on our networking layer as well, where is there a degradation to the amount of connections we can make per second, something like that. So this first one is, the test is to build the 6.1.13 kernel. So this is about 2,700 events per second. So most production workloads won't actually be hitting that many high volume events per second per workload. But what we're seeing here is a really good stress test of what is the cost for Tetragon to observe every single process happening. And what we found was it was actually less than 2%. It was 1.6%. And this is just observing everything. If we want to transfer this event into JSON format, it's less than 1% higher. It's 2.4% to turn every 1.5 million events into something like this, if you want. So incredibly powerful at around 2% overhead is exactly what we're aiming for. Being able to offer that deep visibility, that deep context, but at a relatively trivial amount of overhead. The next one actually gets even lower overhead when we're talking about file monitoring. So I'm not sure how many of you from platform engineering or security engineering side of things have tried to deal with file monitoring at scale. I know in my own time of dealing with it, it was quite hard to do file monitoring at scale just because of the high volume of in-out activity that can happen on workloads. Trying to do a deep umbrella of file monitoring can be pretty difficult. Maybe you'll kind of choose protected paths. Maybe you'll kind of like slim your scope down, but it can be pretty costly. What we found with Tetragon is by pushing all the logic into the kernel, we're able to observe all this file activity that's happening without having to take action on it. So in this benchmark, say we have 1,000 reads and then we sleep 1 nanosecond, but we're not actually creating alerts. For all 1,000 of those reads, Tetragon is monitoring those reads, but it's not creating any overhead because it's not actually moving an event into user space. It's just the cost of observing is only 0.21%, which is honestly at scale pretty trivial. You can monitor 1,000 reads for 1 nanosecond at this low of overhead. It's actually crazy. The next 2 are going to be the TCP CRR tests, and we did this in 2 ways. We did the first one where we're monitoring high volume traffic, and the second one where we're logging high volume traffic. So this first one is going to say, what is the degradation cost on my connections per second for observing and looking at all of my connections? I don't want to actually take action. I don't want to move it into user space. What's just the cost of looking? The second one is going to be, what's the cost of giving me every single event? And what we found was the cost of looking is less than 6%. We're sustaining around 26,000 connections per second based off of the original 27,000. And the comparison we had here was with another kind of cloud-native security tool. That one was around 15%, so around 3 times difference, which is pretty big when you're looking at production environments. So this is just the cost of looking, is being able to sustain still that 26,000 connections per second mark. Now we want to know, okay, well, what's the cost of logging everything? Give me everything in that JSON format. Don't drop anything. Let's really manage that ring buffer. This one, it's still actually, it's a lot higher. It's 17%, and then the comparison is around 25%. But I still think strongly that sustaining that 23,000 connections per second mark while piping everything over is actually phenomenal, especially in Kubernetes environments where you have so much high volume network traffic going on. So this is the benchmarking section done. I'm happy to dive into these more, talk to you more about what we did to set up, what kind of tests I ran. For these, obviously, it was just netperf, TCP, CRR, but I can also tell you about the other ones as well. All right. So with about 10 minutes left or so, I want to spend the next few minutes talking about the XC util CVE. So hopefully all of you have heard about this. If not, it's phenomenally interesting. I think it's one of the perfect CVEs to go viral from the social engineering aspect to the technical aspect. It's really just a fascinating case study and how some of these malicious threat actors and APT groups move to try and embed themselves in open source projects. So stepping back a little bit, there's the XCutils library, and XCutils is a compression library. One of the most common tools out of it is the libelzima library, and this is pretty widely used. Most softwares will have this in some form, and OpenSSH happens to use it sometimes as a dependency. What happened was over the course of a couple years, this person embedded themselves into the XCutils open source project and became a maintainer for the libelzima library. And recently in February, it was found that there was a backdoor in the 5.60 and the 5.61 updates. So what this did is it allowed this malicious user to activate remote code execution when you used OpenSSH in conjunction with libelzima. And Thomas Rochia put together this cheat sheet on Twitter. I'm not sure if you've seen this before, but I highly encourage you and give all the credit to him for this amazing breakdown. There's like a really interesting breakdown of how the script works. Because libelzima is used quite frequently in a few different software as a software dependency in quite a few different applications, it's really just waiting and listening for this OpenSSH dependency in certain conditions around like x86 or x64 distros. So really interesting stuff. But what I want to talk about is how Tetragon and eBPF comes in. So when something like this, like a new CVE comes out, it can often be a wait and see game of what should I do from the vendor? Do I need to roll back? Do I need to update? And there's this time game of, you know, how much time is ticking before an attacker can actually exploit this in production. With eBPF, though, you can write policies in a matter of minutes or moments or within an hour, have a policy written and tested and in production, monitoring for this specific use case. And that's actually exactly what we did. We found the policy, I think it was actually around February 29th this was released, and over that weekend, we were able to get this rolled out to quite a few of our production users, and I'll walk you through the actual policy itself. We wrote a blog on this if you're interested more in the background of the XCutil CVE, how it works, what the exploit is, the breakdown of the conditions of the script. But here's some of the fun stuff around the actual tracing policy. So what we did is we wanted our tracing policy to sit in the kernel and monitor for OpenSSH starting. And when OpenSSH starts, sometimes it'll call libelzima as that software dependency. We wanted to check immediately, is it a vulnerable version? If so, send me an alert. Because we talked about enforcement earlier, you can also say, if this is a vulnerable version, kill the process, kill the signal, do not let this start. For this one, the one we published publicly, we didn't want to send enforcement out into everyone's environment, so we just did a match action down here that says post. This is where you would be able to put like sig kill or override or something like this, but this one right now is just saying, give me the alert. So what this tracing policy is doing is it's monitoring OpenSSH in the security mmap. It's looking for this kprobe of, is OpenSSH starting? If so, let's look at this value of whether or not libelzima is 5.60 or 5.61. If it is, give me the alert. And this is just written in a matter of minutes. You can test it in your environment, and you can immediately see, hey, this is sending me an alert every time I open OpenSSH with a vulnerable version. It's not sending me it when it's not with a vulnerable version. And you can also play around with a match action like, let me just go ahead and share like this, where you can override the value, or you can do a signal kill or something like that. So it's pretty easy to modify this and make the match action something that would actually do inline enforcement. So with that, I do want to pause for a moment and open it up to questions, because I think we're almost at time. Is that correct? But while I'm doing that, I will leave this quote up there. I think it's easy for me, from my position, to say, hey, this is what's exciting about Tetragon. These are the core principles around the awareness, the low overhead, that simplified observability piece. But I think it's so much better to have someone who's actually using it in production to kind of share their experience with it. So I'll leave this quote up there from Jason Satina, who's a staff security engineer at GitHub. But I think this really puts together the values of what Tetragon is right now, the values behind the project, and where Tetragon and eBPF are headed from a security perspective.
Thank you. Thanks, Jeremy, for your insights about Tetragon. Do we have any questions here on this side? We have some time left for Q&A. No, not at all.
No questions?
No questions?
Yeah, go for it.
Okay.
Actually, my gut feeling is everything you have shown us are containers who are more or less so totally full with trash that they should never be deployed to production. So what you have, for me, I would have done pressure to the developers not to deliver a netcat or a curl or whatever. This is something you are trying to repair things which shouldn't have been damaged by developers. So the developers here have done an incredibly poor job to deliver these containers. So how do you handle this? Is this something you would support, or?
Yeah, so the question is asking about what if the problem is pre-production? What if the problem is with what's being developed and what's being shipped and built in the image itself or in the container itself? So that's a great question. I think it's not a core use case of eBPF or Tetragon itself. eBPF is concerned about working at the kernel level, working at something that's in production, something that's about runtime security. So this is kind of correcting the mistakes of the past, or fixing something that can't actually be brought down. You know, quite often you have a workload that you find out is vulnerable, but you can't bring it down for a various amount of reasons. What you can do is dynamically apply a tracing policy. You know, you don't need to restart any container to apply a policy. You apply it and it immediately starts giving you information. So, you know, when you think of like shift left, shift right, this would be on that right side of the spectrum, monitoring in runtime, trying to get as deep as possible and give you as much granular control.
Thank you.
Cool.
Does it answer your question, Thomas? Nice.
Any other questions? Yeah,
yes,
go for it.
there is one.
We're also outside for another hour, so if you want to ask a question or to see anything.
I have a question about kernel versions, Linux kernel. I mean, it's constantly, there are CVEs in kernel. In kernel, so the kernel should be updated quite often. How you check that each and every eBPF, I don't know, policies, stuff like this, are compatible with this kernel? Should we care about it?
Yeah, so that's a really good question. So I forget the exact Linux distribution where BTF, which is the translator between BPF language and the underlying Linux kernel code structure is. But essentially what's going on is when you write an eBPF program, it's translating that into how the Linux kernel would actually read that program and interpret it. And from an Isovalent perspective, we have a translator that can work on any Linux distribution possible. From an open source perspective, I think the BTF translator, I forget the exact Linux kernel, so I don't want to say the exact one, but I think it was like 4. something. I think it's been in there for a while. So, yeah. Hopefully that helped a little bit. eBPF isn't going to solve the CVEs within the kernel, but I think it actually, eBPF from like a higher level perspective helps solve some of the problems with trying to fix things in the Linux kernel which is a more slow-moving beast. You know, the whole idea of eBPF is move fast, try things, test things in your unique Linux kernel environment, and know that it works for that environment, rather than trying to ship things upstream or downstream to the Linux kernel itself, which is more time-consuming, more dangerous to the entire Linux distribution. eBPF allows you to move fast and actually use the verifier to make sure that it's verified to be safe. So any eBPF program will be verified to be safe before you run it. That's a condition of eBPF itself.
Thanks, Jeremy.
Cool. If you have any other questions, we're right outside.
There's still
Come
at
chat.
this point.